Welcome to the silent science where the universe unwinds slowly and curiosity drifts into dreams. Tonight on the silent science, we're venturing into the quiet aftermath of cosmic destruction to answer one powerful question: what happens after a star explodes? From the formation of neutron stars to their gravity-bending surfaces, from glowing pulses to gold-producing collisions, this calm journey will guide you through one of the universe's strangest and most beautiful transformations. Where are you watching?
There's a moment in every star's life when it stops shining. Not slowly, not gently, but suddenly. In a final, brilliant convulsion, it collapses inward, then explodes outward in one of the most violent events in the universe. But what happens next? What remains after the light fades? What strange new form takes shape in the silence left behind? Tonight, we're not just watching stars die, we're following them into the aftermath, into the quiet chaos of cosmic rebirth. Because the end of a star isn't an ending at all, it's a transformation. So wherever you are, curled up under blankets, drifting between dreams, or simply seeking a moment of stillness, join me now on this gentle journey through fire, collapse, and creation. Let's explore what happens after a star explodes. Before any explosion, there is balance. A star lives in a constant tug-of-war, gravity pulling inward, pressure from nuclear fusion pushing outward. This equilibrium lasts for millions, even billions of years. But for the most massive stars, time runs out quickly. They burn hot, live fast, and die young. They begin their lives fusing hydrogen into helium, just like our sun. But unlike our sun, they don't stop there. Carbon, oxygen, neon, silicon, and finally iron. Iron is the death note of a massive star, because unlike lighter elements, iron doesn't release energy when fused, it consumes it, and so the engine stalls. The core cools. Gravity wins. In less than a second, the heart of the star implodes. Temperatures soar past 100 billion degrees. Electrons slam into protons, creating neutrons and neutrinos that flee into the void. Then, the rebound. The outer layers crash inward and bounce off the dense core. A shock wave ripples outward, and the star explodes. A supernova. For a brief moment, one star shines brighter than an entire galaxy. But what survives this cataclysm? What lingers in the wake of such violence? The birth of the neutron star from destruction. Something strange emerges. If the dying star was at least 8 times the mass of our sun, gravity crushes its core until atoms no longer exist. Protons and electrons merge. Neutrons dominate. This is the birthplace of a neutron star. Imagine compressing the mass of the sun into a city-sized sphere. 1 teaspoon of this matter would weigh 6 billion tons. That's not science fiction. That's physics at its limit. It spins wildly, hundreds of times per second. Its magnetic field is trillions of times stronger than Earth's, and yet it sits quietly in the dark, invisible to the naked eye, but it pulses. A lighthouse in space. A pulsar, some spin so precisely they rival atomic clocks, others flare with unimaginable power. But how does something so small hold so much? How can nature create such extremes? Beneath the crust, the quantum kitchen beneath. The crust lies a kitchen of cosmic proportions, not one made of steel and heat, but of pressure and density so extreme that atoms forget what they once were. The outer crust is solid, dense, stronger than steel. Deeper down, things get stranger. Electrons merge with protons. Neutrons drip out like syrup. And then comes the pasta layer. Yes, really, scientists call it nuclear pasta, a region where matter arranges itself into shapes resembling spaghetti, lasagna, and Swiss cheese. These aren't metaphors. This is real physics. Here, the strong nuclear force battles gravity. Matter folds into bizarre geometries, locked in tension. Below that, the superfluid core. Neutrons flow without resistance. Frictionless rivers of matter swell silently, and at the very center, we don't know. Some theories say quarks escape their bonds. Others suggest hyperons. Particles heavier than neutrons lurk in the depths. Even stranger ideas propose that dark matter might accumulate here. Is this the edge of known physics, or the beginning of something entirely new? The magnetic titans, Magnetars neutron stars, have powerful magnetic fields, but some are monsters. Magnetars. Their fields are over a quadrillion times stronger than Earth's, so strong that if one were placed at the moon's orbit, it could erase every credit card on Earth. At these intensities, space itself changes, light bends, time warps. Even the vacuum becomes birefringent, acting like a lens. Magnetars don't just pulse, they flare. Sudden eruptions of X-rays and gamma rays flash across the sky. These starquakes crack the rigid crust like porcelain. Each quake releases more energy in a second than the sun emits in 100,000 years. And yet, they are rare. Only a few dozen confirmed. Are they born only from the most extreme collapses? Or do they evolve from other neutron stars over time? The clockwork lighthouses, pulsars, asterisk of all neutron stars. None are more precise than pulsars. They spin hundreds of times per second. Beams of radiation sweep across the cosmos. To us, they appear as regular pulses, like a heartbeat echoing through the void. Some are so stable, they keep time better than atomic clocks. Astronomers use them to detect gravitational waves, search for planets, and even navigate spacecraft. They are the ticking metronomes of the universe. But how do they stay so steady? And what causes the occasional glitch when a pulsar speeds up ever so slightly? Could it be a shift in the crust, or a sudden unpinning of vortices deep within the superfluid core? Pulsars remind us that even in collapse, order persists, time continues, and somewhere a beam still sweeps the sky. Asterisk when to become one, neutron star merges. Sometimes a neutron star finds a partner. Two dead stars, locked in a dance of gravity. They spiral closer and closer. Space-time trembles. Gravitational waves ripple outward, and then they collide. In less than a second, they merge. A kilonova erupts, a flash of gamma rays, a burst of light, and a shower of heavy elements scattered into space. Gold, platinum, uranium. These elements don't come from ordinary stars. They come from the collision of two neutron stars billions of years ago. Atoms forged in such explosions found their way to Earth. Ring your phone. Your body, you may carry the ashes of ancient cosmic collisions. And in 2017, we saw it happen. GW 170817-. The first observed merger of two neutron stars, light and gravitational waves, arrived together. Confirmation that theory matched reality. But what else hides in these mergers? Do they sometimes briefly form hypermassive neutron stars before collapsing into black holes? Are they factories for exotic matter? Are they the key to understanding the strongest forces in the universe? Listening to the universe, how we study neutron stars. Neutron stars are silent to the eye, but they speak in many voices. Radio waves, X-rays, gamma rays, gravitational waves. We listen with machines, with radio telescopes scanning the sky, with satellites orbiting above Earth's atmosphere, with detectors buried underground, waiting for ghostly neutrinos. Each signal tells a story. A pulsar, timing its beat, a magnetar flaring in fury, a kilonova lighting up the dark. And in 2017, we heard two voices at once. A chirp from gravitational waves, a flash from light, proof that Neutron stars are not just objects of study, they are storytellers. They whisper across time. They sing in frequencies we've only begun to hear. Asterisk. The poetry of collapse. Neutron stars in culture and imagination. Neutron stars may seem far removed from daily life, but they've shaped human imagination. Arthur C. Clarke imagined a wrench surviving a neutron star encounter only to become a pun-filled relic. NASA sent pulsar maps aboard. Voyager to guide alien explorers home. Poets write of stars that die but still pulse. Philosophers ponder what remains after collapse. Are neutron stars endings? Or are they transformations? They are the echoes of ancient fires, the rhythm of the universe beating in silence, and perhaps, in some distant future, they'll serve as navigational beacons for travelers beyond our solar system. They are tiny, yet they hold more than we understand. They are dead, yet they pulse with life. Asterisk, you are made of starlight. Word count, you are made of stardust. Not metaphorically, literally the carbon in your cells, the calcium in your bones, the iron in your blood, all forged in the cores of stars long dead. And some of those stars ended in supernova. Some became neutron stars, some collided, scattering gold and platinum across the galaxy billions of years later. Those atoms formed planets, oceans, life, you. So when you look up at the night sky, remember, you are not separate from the cosmos. You are part of it, born from the same fire, made from the same collapse, and maybe, just maybe, you are made to wander, the quiet pulse of the universe, as we close tonight's journey. Let's return to the question we asked at the beginning. What happens after a star explodes? Now we know it collapses, it transforms, it pulses, it collides, it scatters the seeds of life. And in the silence left behind, something beautiful remains, a neutron. Star. Tiny, dense, ancient. Still spinning, still listening, still waiting. And so, wherever you are, and whatever time it is in your corner of the cosmos, breathe slowly. Look up. And remember, even in the darkest corners of space, the universe keeps turning, and so do you. Good night.
Transformations. Where are you watching from, and what time is it there? I'd love to hear in the comments. It's always a joy to see how far these peaceful stories travel. If this helped you unwind or stirred your curiosity, feel free to like the video and subscribe for more gentle explorations of space, science, and sleep. Wishing you a restful night under the quiet pulse of the stars.